infectious diseases and vaccines. We're going to skim through a little bit of this to try and get to the more, the vaccine portion of this, but in order to understand vaccines and understand how they work, what they target, you have to understand the infectious diseases themselves. And you'll see that this is very much the case when we're talking about things like the flu vaccine, which is pretty complicated. So, you know, we have vaccines for things like polio, which we basically have been able to eradicate polio with a vaccine. But then you have things like the flu, where every year you get your flu vaccination, but yet we still have flu. And we have things in between. We have HIV, which we still don't have an effective vaccine for. And so why can we eradicate polio but not HIV? And some of the, talk about some of these things. You know, in that case, we're talking about viruses. What about fungi? What about bacteria? You know, so what we need to kind of know, what part of the immune system do we need to induce protection with? And this can be based on the types of infections themselves. So first, infective agents have to overcome our physical barriers. They must breach the skin or get into the epithelial linings of the skin or the gut. One of the easy ways for things, bacteria or viruses to enter is through the stomach, because we're constantly eating things. And breaching pathogens encounter, the first things they encounter, remember we talked about different antibodies. Who remembers which isotype, which class of antibodies line, for example, the linings of the gut and respiratory passages and mucous membranes? Who remembers which IG that is?
IgM.
IgM can be one of them.
IgA.
A, there you go. First of the alphabet A. So we've got IgA, which is secreted. So, and then it lines these passageways. So the IgA is our first, basically, defense against these to kind of block them from binding. And then we have other mechanisms, and we talked about innate immunity. And so pathogens have to overcome a lot of these things, and we'll talk about how they do that in a sec. And then those pathogens are either cleared or killed by the host, but sometimes they do survive long enough to spread from one host to the other before they are cleared. And that's the case, for example, like with flu, things and chronic illnesses. Viruses typically enter the host through a cell surface receptor. So this is where if you block something that's going to bind to a surface receptor with an antibody, then you can prevent the initial entrance of virus into that cell. So again, viruses, and that's how they're selective as to what cells they bind to. So again, some viruses bind to an epithelial cells, the lining of your lungs, or some viruses will infect cells in the central nervous system. Some will, and this is based on surface receptors. HIV, for example, targets it targets more than just CD4s, but one of their targets is CD4 cells themselves. So, and that's a big problem because the best cells at preventing viral infections and eliminating virally infected cells are going to be those T cells. And so if we can get rid of T cell health by infecting the actual cells that are going to mount the response, then we are preventing basically our cellular response against the virus. And so that's why HIV is so dangerous, because not only is it hugely mutagenic like the flu, we don't clear it seasonally like we do the flu, because HIV can infect CD4 cells, and those are the cells that are going to help mount a response that will actually remove that virus. So the HIV and the flu are very similar in some aspects, but in other aspects they're different. And that's based on the cell surface receptors they can bind to. Obviously, viruses are more likely to thrive if they don't kill a host, because that's going to increase their chances for replication and spread. But during replication, viruses trigger humoral and cell-mediated adaptive immunity mechanisms. So that's what happens. So many viruses are also neutralized by antibodies. So viruses have to leave the cell to infect other cells. They have to enter cells. So antibodies are a good way to help prevent binding. And so that's a lot of our vaccines against viruses are actually inducing antibodies versus a T cell response. So examples include preventing influenza virus from binding to their target on residual cells, and then production of that antibody that binds to poliovirus prevents it from attaching to those cells. So you can either block it binding or entering the cells. Now again, as you know, antibody can't target cells when they are inside, or can't target virus when they are inside the cells, and that's where you need helper T cells and cytotoxic T cells. So again, and viral viruses that are replicating inside the cell are making viral proteins. Those proteins are going to be recycled, processed, presented via MHC, and help induce a T cell response to those. And those T cells, those cytotoxic helper cells, will then help induce cytotoxic cells, the CD8s, and then will go and kill cells that have been virally infected, secrete things like interferon gamma, which is going to directly induce an antiviral state in all the cells in the region. And in that way, and so most of the time clearing of viral infection, so whereas antibodies are great at helping to prevent further infection and helping to prevent the initial infection, clearing of virus is very much dependent on CD4s and 8s. People who are then are compromised, immune compromised, or for some reason deficient, and this mechanism cannot easily clear virus.
Do antibodies or cytotoxic T cells, or helper T cells end up neutralizing any toxicities that are secreted by the viruses?
So the T cells themselves would not be good at, so for example, the virus has a toxic protein, which is the case in some viruses, that would induce anaphylaxis, then no, T cells themselves will not be really good at neutralizing that, other than to eliminate the virus itself. So yeah, and that's where antibodies will come in. So viruses employ several different strategies to evade the host defenses. Some examples, and these are good to know: hepatitis C overcomes interferon antiviral effects by blocking PKR, so this will then block that whole pathway. HSV inhibits TAP activity, so basically shutting down MHC class 1 presentation to CD8. So remember, TAP was that protein that allowed protein or small antigens to enter into the ER and then be processed without TAP. If you block that, you're going to block entrance of antigens that get chewed up by the proteasome into the ER, and then you don't get it. Basically, you're hiding, those cells are now hiding. Luckily, in some of those cases, by blocking TAP, you're also affecting MHC class 1's ability to traffic to the cell surface, and then NKT cells can come in and see that those cells have low levels of MHC class 1, and so we do have some ways to respond to those type of events. Adenovirus, CMV, cytomegalovirus use similar strategies. Measles virus, HIV inhibit class 2, so not only does HIV infect CD4 cells, but they also downregulate class 2 expression and presentation to other helper cells. So HIV actually infects other cells than T cells, and in those cells it downregulates class 2. So you may get class 1 presentation, but without T cell help, without CD4 help, you're not going to mount a response. In fact, you'll probably mount more of a tolerogenic response, and that's why HIV is so chronic and it's so hard to get rid of. Some viruses code for anti-complement proteins. Other viruses constantly change their surface antigens. That's like the flu and influenza virus. This is why it's constantly, you can get flu year to year because it's always changing its surface antigens. So speaking of flu, influenza has been responsible for some of the worst pandemics. And there's three, so when we talk about flu or influenza, we're talking about three basic types. A is the most common, and this is the one that, for example, can cross species. For example, bird flu, swine flu, these are all type A types of viruses. B and C are less common, probably because they don't cross species, and that crossing species sometimes allows for more virulent strains to arise. And so obviously those are the strains that are going to survive the best. Two key viral glycoproteins are hemagglutinin, HA, and neuraminidase, NA, so we'll just call them HA or NA. So for example, remember when you have a virulence or bird flu or something, they say H1N1, this is what they're talking about. These are, the H1 is going to be a hemagglutinin 1, and the N1 is going to be neuraminidase 1, and these are going to be different, I guess, alleles or different forms of that same protein. So they, also another issue is that these are RNA viruses, so some viruses are DNA viruses, single-stranded DNA viruses, single-stranded RNA viruses, and in the case of single-stranded RNA viruses, these tend to be very mutagenic, as RNA is less stable than DNA, and they don't have, also these, the flu viruses don't have proofreading like we have, and so the rate of mutation is very high, and also the fact that they have 8 single-stranded RNA segments, they can swap those segments between each other, and that also increases the basically the variation in their genetics, which is also an issue. And so, influenza, let's see, properties of the influenza virus. Again, also the other thing to keep in mind is some of the ways that influenza is difficult to get rid of or difficult to make a vaccine for is it's fairly simple. It has one surface protein that allows for attaching to cells, and the other allows it for escape. So it has a simple mechanism, and it doesn't have a lot of unique antigens on its cell surface. Its unique antigens, again, would be this HA and the NA, and it has multiple variations of those. Every year, you're going to have new combinations that arise, and people are not immunized against them.
So you mean, this 8 segment that they can swap partially or just whatever?
So if you have a cell that's infected with 2 different variants and they have different segments, they'll swap those
So you
segments.
don't know, you cannot predict what's coming next.
You cannot predict 100% what's coming next, but then CDC, for example, and WHO are tracking the genetics of what has infected people, so they can see it evolve, the flu strain evolve over time, and then they can get a rough idea. So how they make the flu vaccine each year is they're going to try and predict what variants or what H and N are going to arise the next year, and they also have to, what we're going to talk about in just a sec, They also have to make sure that the vaccine, the new vaccine is different enough from the old vaccine, because we're going to see that there's, if they aren't different enough, then they actually will just boost the previous response. And if the previous response is to an antigen that isn't expressed this season, then you, in effect, the vaccine is useless. So it's, we'll get there in a second. So each strain is defined by the host of origin. For example, did it originate in swine or avian? Strain number, they give it a strain number, the year it was isolated. So here's, for example, an example, strain A. Most of these, again, start with A because these are the ones that tend to be more virulent and cross species. And these were some strains that they tracked. Where did it start, or where did they first identify it? Puerto Rico, for example. Given the strain designation 8, that means that it was the 8th isolate that they found it in, and then 34 would be the year. And so you can see 2009. Here we have one that was in California, strain number 4. And so this is how they would designate those. And so what do you get? You get different variations in epidemic influenza strains, antigen drift. So the first thing we need to, and this is going to be on the exam, what is antigen drift? Occurs due to high mutational potential. So the first thing that makes the flu hard to vaccinate against is it's highly mutagenic. Those RNA are, every time a virus replicates, it's getting new mutations because it doesn't have any type of proofreading when it replicates its DNA like we have. And so every time you get a new mutation, that's called antigenic drift, and they have a lot of antigen drift. So again, different types of H's, HAs, and N's are going to be expressed. And so if we develop an immunity against H1N1 or whatever we're going to call it, then we have H2N2. Now those will escape. We won't have antibodies that recognize those, and those can infect cells. So another word is antigen shift. So this is when different virus strains infect the same cell, and so as we said, there's different strands of RNA that are easily swapped. So the RNA genome segments can be swapped in new virus. This is called antigen shift. So that's another reason these are highly mutagenic, because they've got nice compartmentalized genetics that are in very swappable sets.
So is the drift and the shift, which one is more different? Is more change?
I don't know.
No, you haven't know.
I have
It would
to
be
know.
a shift.
No, which one you have more? I thought the drift is small, but the on the slide you didn't say that. It's a big.
Well, they're both big changes. It's just we're swapping genes in this case. We're changing the actual genes in the other case. So we're swapping more information here, changing more information, but in the other case we're developing new antigens themselves. And so they both contribute, and you don't need to know which one contributes more, but they both contribute to the virulence and the ability of influenza to escape.
I thought it's a drift, then shift.
It could be. I don't know what the rates are, but I don't.
You know, that's
It's not that important.
Shifts are less common.
Yeah, but it's so much changing.
So those viruses would have to infect the same cell at the same time.
Yeah.
So another thing to take into account is this, and this is pretty important when developing a new vaccine, is the idea of this original antigenic sin. So again, most of our vaccines, our flu vaccines, are inducing antibodies against flu. and this is for a couple of reasons. Again, usually when our own body, our own immune system removes the flu, so you know you get the flu. And how long does the flu usually last? How many days?
A week.
Yeah, so what does that tell me? What does that tell me? What cells are actually getting rid of it? Or what system, what part of my immune system is actually getting rid of this flu? The adaptive arm of the immune system, because it takes 7 to 9 days, so it's probably part of the adaptive response. It's definitely not a memory response. If it was a memory response, I'd be sick for like 3 days, 2 days, depending. So if I have some previous memory, that's gonna, and in some cases you might have that, because you may have memory that still recognizes certain antigens on this year's strain. So you might get lucky and have a real mild case of the flu. So you know, oh, I had a memory response, great. If it's 7 to 9 days, you're probably mounting a primary adaptive response and removing that. So most of the vaccines are actually trying to induce antibody responses, prevent you from getting the virus in the first place. And so the vaccines that you're getting are inducing these antibodies against these attenuated viruses they're using. So they have to decide, well, which virus are we going to give you? Which attenuated virus are we going to give you? Which H's and N's are we going to give you? And what happens is, if I have, let's say I have strain A, we have antibodies that bind to strain A, and then we have, in this strain, we have A and B, well, A, B, and C, let's say. So we have antigen A, B, and C. As long as I have a response against A, I'm not going to mount a response against B or C, because our immune system, what will happen is the antibodies against A will bind to this target. And when a memory cell sees that, it's going to proliferate and make more antibody. But when a naive cell sees that, because the cell is already coated with antibodies, the FC portion of those will bind to this naive cell. So here we're seeing that memory cells respond differently than a naive cell, because this naive cell, if it sees that, well, I'm recognizing something, but it already has antibodies on it, so I don't need to mount a response because I already recognize this as foreign and not. And so you get what's called original antigenic sin, where I've already encountered this. I don't need to attack it anymore. I don't need to mount a response. So what will happen is you'll get, the virus is going to vary from season to season. Your second infection, this virus still has A and B, so you mount a memory response. You're still mounting a memory response because it still has A here, but then once it shifts and it no longer has any of these, then you're going to again mount a primary response because you have no antibodies bound to it. So if I was to, for example, if this was what we saw and we gave you a vaccine A, B, C, next season if I give you a vaccine with D, E, and F, let's say I knew that this strain was coming, and I give you a vaccine with A, D, E, for example. Well, I'm not going to mount a response against D or E because those have A on it. So that's the other thing they have to take into consideration is when I make a vaccine, I have to try, if I'm assuming that I'm going to get C, D, E, and F, and I'm not going to have any A or B or C, I don't want to include A if it was in the previous year seasoned virus or the vaccine, because I'm only going to induce antibody production against A. And so, again, each year they make a new batch of vaccines, which basically targets 3 separate strains. And each of those strains has to be different enough from the vaccine than the previous year, so I don't just reinitiate that initial response, especially if I don't think that the new virus is going to have one of those antigens in it. So it's a little bit tricky developing vaccines for the flu. And so that's one case. And the flu is the example we gave. HIV is also RNA based. It is also highly mutagenic. It has additional negative aspect in that it infects CD4 cells. So the immune response now let's cover bacteria. Antibodies provides strong mechanisms for eliminating bacteria. Again, when we're talking about bacteria, most of the bacteria are going to be extracellular, but some bacteria will get inside cells and proliferate within the cells. So some mechanisms work great for extracellular bacteria, but there are some intracellular bacteria where antibodies aren't the best target for them. And so we have to keep in mind what those are. Bacteria have evolved to also help to overcome immune responses. So, for example, they have evolved to block. So IgAs are our first defense against bacteria. So some bacteria have proteases that cleave off the basically the heads of those IgAs at the hinge, and those IgAs are no longer going to block it binding to cells. So some bacteria have evolved ways of getting past that IgA blockade. They can also prevent, some bacteria are really good at preventing themselves from being phagocytosed. They build coats around them, sugar coatings around them. They will downregulate their surface markers. They will coat themselves with self-antigens, proteins that are self-proteins so that we don't see them as foreign. They'll block complement. They will block antibody-mediated agglutination, so they secrete things that block that process. And so basically, they're able to overcome immune responses in that way. Tuberculosis is an example of bacteria that is primarily controlled by CD4 cells. Again, we know this because in individuals that are have CD4 defects, in people with HIV, we see a huge problem. Tuberculosis grows out of check, and so it can spread easily, and it forms these granulomas and called tubercles. So basically, it's pretty straightforward that we can tell that CD4 helper cells are really key factors in helping to control, but through macrophages ingesting it. And again, how do CD4s help in this case? In this case, they're not inducing cytotoxic T cells, CD8s, but here they're actually helping macrophages to come into the area. So they're becoming inflammatory mediators to where they're producing interferon gamma. This interferon gamma activates macrophages. It ingests and destroys the microbes. So in some cases, CD4s are still really important in removing even bacteria, even though they're not intracellular. And if macrophages are eliminated or can't eliminate the microbe, then you get chronic inflammation, and this can lead to, as we've talked about, long-term effects, loss of tissue damage. Diphtheria. So here's a case where diphtheria itself isn't actually toxic. It's actually it's a virus. It's a bacterial virus or a phage that infects the diphtheria itself that has this toxoid that causes damage. So diphtheria is controlled by immunization. In order to immunize against it, we actually immunize with the toxin. So with the toxin itself. So we We would give you a non-damaging form of the toxoid. So, for example, a portion of that toxoid can be given, or the toxoid itself can be denatured so that it's not damaging. Another toxoid that we immunize people with is Tetanus Toxoid, and so you're actually getting the toxin, the tetanus toxin, which is just going to be a non-damaging form. They denature it, or they give you a portion of it that's not damaging, and that's what you're mounting an immune response against. So in this case, we basically will give people what's called a DTaP early on, and this is for to immunize against diphtheria, tetanus, and whooping cough. And so these basically, it produces antibodies that bind to the toxin and neutralize its activity, because the toxin is what actually does the damage. These are also, well, let's see, I think we'll talk about that later on when we talk about emerging infections. But so we've seen recently a lot of increase in instances of whooping cough. So we've seen a reemergence of some of these illnesses, and this is because people aren't getting boosters. Also, when we give these, initially when we gave the DTaPs, we were giving one, and because it was early on and babies still had the mother's immune response, or still had passive immunity from the mother, which means antibodies from the mother for these things, they did not mount a really robust response against the vaccines themselves, because there were already antibodies that bound to these toxins. And so people who only got one of these were actually getting these diseases later in life. And so they kind of upped the number of times you got your DTaP. I think you get it early on in life before 18 months, and then you get it again at 6 years. And they recommend to actually get a booster every 10 years now. So protozoan are another parasite. Again, who remembers what IG is really key in getting rid of parasites? IgE. So the same one that causes causes allergies is really key in removing these parasites. So some of those, an example would be malaria. This is the number one cause of parasite-induced death worldwide. Why is malaria so hard to get rid of? It moves, one, it has different stages of its life cycle. Immunity is poor in children under 14, maturational changes allow antigen shifting. So at one stage they have one set of antigens, and then they change completely into a totally different organism, have different antigens. So this makes it hard to mount an immune response, because once we've already mounted an immune response against maybe the initial form, then it's the organism's changed and it's expressing different antigens. It also hides inside.
Is malaria like a bite, mosquito bite?
So it's the mosquitoes that basically the vector that transmits it. It grows and lives within the mosquito. The mosquito bites you, you get infected with the spores, and then they will hatch and grow in the liver. Then they will infect red blood cells. Red blood cells are a great place to hide because they can prevent getting bound by antibodies. And one of the major ways that we get rid of large things like these worms is through IgE, but IgE can't get into the red blood cells, so that's one way they hide. Red blood cells aren't really good at antigen presentation because they have a job to do, and so red blood cells are a pretty safe place for those to hide out. And then they have a short blood circulation time. A free parasite stage prevents good immune stimulation. So they kind of just are evading the immune system in a lot of different ways. They also shed their outer coat, and this also prevents antibody from binding and killing the worms themselves. And now that drug resistance is becoming a problem, people people are trying to develop better vaccine strategies for these. Protozoan, so another protozoa is African sleeping sickness caused by two trypanosome species transmitted by tsetse flies. And here's where the protozoan differentiates and divides every 6 hours. So again, making it very hard to mount an immune response. They move from blood to the central nervous system. This is where the sleeping sickness comes. And they express one VSG gene at a time, which is going to be a good target for the immune system, but they're constantly changing that
What's
over
a
time.
VSG?
Viral, or I mean, something. You know what? I don't know. You'll have to look that one up. This is definitely not my field of expertise, but so if anybody wants to look that up, go for it. I'm sure everybody has a smartphone. Expresses one VSG, so they only express one of these genes, one of these proteins at a time. So basically, if you look at times after infection, this is changing from one. So in order to mount an immune response, we would have to already have memory against all of these. So another protozoa that can infect is Leishmaniasis, and this lives in macrophages and phagocytomes. So it actually lives within the cells, which makes it hard to eliminate. Transmitted by sandflies, produces one of two syndromes, either localized cutaneous, this is self-resolving lesions, or systemic visceral leishmaniasis, which is nearly fatal without treatment. And the removal is mediated by a Th1 response against this is a helper response, and interferon gamma secretion in individuals who are skewed to a Th2 or antibody response are less likely to resolve this. Again, being intracellular, it's easier to target those cells with a cytotoxic or a helper response.
How do
An
they
antibody.
listen many answers?
Mhm.
Yeah. What kind of vector is that?
What kind of what?
Vector. How do you get it? How do you get the disease? How do you get the
Sandflies.
sandfly?
Yeah. So a lot of these, another example are helminths. These can enter through the intestinal tract, so they'll form spores. They will be in food that you eat that is not cooked long enough. They can get in through the intestinal tract. These are extracellular. They don't replicate in hosts, limiting an immune engagement. They may decrease external antigens, so they they'll wrap themselves in host proteins to further limit immunity, so they kind of will disguise themselves. IgE, it can be important in preventing them, but also Th1 responses are important in inducing macrophage activation and elimination of them. So fungal infections are another example.
So,
Yet again.
excuse me, can I say something?
Uh-huh.
When you say induction for Th1, IFN, interferon gamma macrophage, that means they are Th1 positive IFN gamma positive macrophage or something?
So the T helper cells start secreting interferon gamma, and this interferon gamma, aside from its antiviral activity, also has an inflammatory effect of inducing macrophages. Those macrophages are now going to. So in this circumstance, because we've talked about how IgE is so important for getting rid of large organisms, and how, but in this case, helper cells are actually inducing macrophages to kind of engulf these cells or to degranulate and make a toxic environment. So it's kind of a mixture of innate immunity, but induced by the adaptive immune system. So
I thought for this helminths is IgE, the basal cell, and also whatever, you don't know.
it is
Master cell,
it is for most
degranulating.
of them, but in some of them because they're able to hide or cover themselves, for example, then it then becomes actual Th1. Th1s actually are important for removal of some of these. So not all of them are easily removed by IgE.
Remove helmets, not
So yeah, so again, fungal infections. I'm not going to go over this because it's not really important for you to know how we classify them. The important thing to know is most fungal infections are controlled due to PRRs on innate immunity cells, keep fungal cells in check. Also, commensal fungal organisms help to crowd out pathogenic fungi. So we have our normal flora, we have fungal cells, yes, on our skin, in our body, and normally they're kept in check by the healthy ones. That's when, for example, you take antibiotics and you clear out a lot of the normal flora that now you can get pathogenic fungi that will grow out of control. And because they have no competition for resources and can grow out of check. And the important thing, part of the important arm of the immune system to remove them is going to be phagocytic cells that will help take up and remove these cells. They also have evolved evasion mechanisms, capsules that prevent receptors from binding, fungi-induced expulsion from macrophages, so they might get taken up by a macrophage, but they develop mechanisms to then be released by macrophages, thus escaping induction of inflammation, and so they prevent kind of that initial inflammatory response, and so they can be hard to deal with. And we do know that immunity against fungal pathogens is acquired, and how we know that is because evidence is HIV patients who basically aren't able to mount a good CD4 response. You see a huge increase in fungal infections. So it's lots of fungal infections in HIV patients that have to be kept in check. And how do we also know that it's part of the adaptive response that really helps keep them in check is because B-cell deficient mice, for example, have no increase in susceptibility. And so we know that pretty much it's the adaptive arm of the immunity keeping these viruses in check. It's not the B-cell arm, not the antibody arm that's helping to keep those in check. So observations indicate that, again, a Th1 response is very effective at controlling fungal infections, as opposed to Th2 and Treg responses are tied to increased susceptibility to such pathogens. So again, here's a case where the Th1 response is going to be really key. Even though this is not fungi are not intracellular, we're still reliant on a Th1 response to keep it in check. We have a lot of diseases that are emerging. I'm not going to cover this. Some strains are more virulent than others because they tend to bind more strongly or be more effective at entering cells versus other forms. So again, different variants can be more virulent. And we've seen, outbreaks of Ebola, Legionnaire's disease. So this isn't even up to date because we've had even more recent outbreaks of some of these. So reemerging, why do we have reemerging diseases? Well, so we see combinations of diseases, for example, HIV and tuberculosis will then lead to other types of infections. HIV makes you more susceptible for fungal infections, for basically everything, because we're getting rid of that CD4 response. Improper antibiotic use is leading to more antibiotic-resistant strains of bacteria. It's also leading to, again, normal control from our normal, basically, normal flora is once that's removed, a lot of these pathogenic variants are able to replicate and divide unchecked and then infect other people. So basically that improper antibiotic use is leading to a lot of emerging diseases. And also the laxity in our vaccination program adherence.
What's laxity?
That means that we're not taking our vaccines as serious because we haven't seen these diseases. And so it's easier for people to say, well, there's a risk to being vaccinated, a slight inherent risk to vaccination, and therefore I'm not going to take that risk because everybody else is vaccinated against this and I don't need to, because how am I going to get it if everybody's vaccinated? But enough people
Herd immunity.
enough people have done that to where we've had whooping cough outbreaks, we've had them in Gainesville, we've had diphtheria reemergence, we've had measles outbreaks, the Disneyland measles outbreaks. So these are coming back because we're not keeping the herd immunity up. How do we vaccinate people? There's two main, so let's break them again. Passive versus active. Passive is when I'm not inducing an immune response. I'm just giving you antibodies, for example, Igs. Passive immunity is passed on through the nursing, through infants. It can be, you can have IG. If you're going to somewhere you've never been and you don't want to get sick because you haven't encountered all the variants of pathogens in that area, you could get IG immunoglobulin shots from people in that area. So they're passively immunizing you against what you're going to encounter. So you're going on vacation, it might be a good idea to ask your doctor, hey, can I get an IG shot because I'm going to wherever. And so you can do that and have passive immunity. That'll last for, probably last for your trip, depending on how long that trip is. Another example of passive immunity is you get bit by you were in Florida, there's lots of venomous snakes here. I'm sure that the hospitals keep anti-venom on stock, hopefully. You get bit by a snake, and they're going to give you passive immunity. They're not waiting around 7 days to induce an immune response. They're going to give you the antibodies that are going to bind to that toxin and inactivate it and block it from binding to receptors and doing damage. Let's see. Active immunization. So here's an example of some active immunizations. These are where we're actually giving you either an attenuated virus, we're giving you an attenuated toxin, we're giving you various different, maybe we're going to give you proteins from that virus or something that's going to help induce either an antibody or a cell-mediated response. And so, for example, the case of tetanus, we're giving you Tetanus Toxoid. Some of the vaccine that we give people not only induces an antibody response that's going to help to bind to that toxin, we actually are also inducing T-cell response. So if you've ever wanted to have a good model for looking at a T-cell response, you find somebody who's been vaccinated against tetanus recently, and you can take their T-cells out, and you can take dendritic cells out of that same patient. You load them up with the same toxin, Tetanus Toxoid. They chew it up, present it on their cell surface, and you can see a gangbusters T-cell response against those. So those are so a lot of these are mounting both antibody and T-cell responses. We've got like Hep B, Rotavirus Vaccines, and this is kind of looking at a lot of these you see there's boosters that are given in multiple different stages. So again, we give boosters because maybe the initial, we're trying to protect infants from these diseases because they're more immune suppressed, they don't have a robust immune system, and we want to protect them, but the response that they have to this is a lot of times not as robust as it would be later in life. So a lot of times we'll give them that initial one to help them keep from getting an infection, but then you have to give them a booster later in life once their immune system doesn't have that passive immunity given from their mother that's going to kind of help to limit that response. So again, boosters are sometimes because that initial, you can't rely on that first initial vaccine because in a lot of cases it's not really going to lead to good long-term immunity. So make sure to get boosters for your children. So active immunization can, so here, like for example, small measles outbreaks in recent years are due to the drop in herd immunity levels. They found that a lot of the people who, the majority of the people who got the measles, it was either due to not getting the vaccine at all or actually getting the vaccine, but they only got that initial dose. And so, they think that the reason those people still got measles is probably because lingering maternal antibodies, because the parents were vaccinated against it. They had titers of that antibody. It was in the milk, it was in the child. So when that child got that measles, that initial measles vaccine, again, remember that antigenic sin, that the cells were bound to antibodies and they didn't mount as strong or robust a response against measles, and so they didn't have protection later on where we see these outbreaks. So there are several vaccine strategies. Here's where we get into, and we'll finish up with talking about what are the different strategies. One, they should be safe. So when we're looking at trying to develop vaccines, we're trying to develop safe vaccines. They should be effective at preventing infection, obviously, and delivery strategies should be achievable in desired population. Some issues with these are how do you deliver a vaccine if it's not stable unless it's refrigerated in a country where you don't have a lot of refrigeration. So other things to consider is how do I keep this an effective vaccine? A lot of times these are cellular vaccines or proteins, and these proteins, in some cases you want to denature like a toxin, and so you still have, it's a balance between denaturing that toxin but still being able to induce an immune response against it. But also, in cases where you are going to places that don't have refrigeration, you want to make sure that this vaccine is still effective even if it hasn't been, per se, refrigerated.
So what's the table?
This table is giving some examples. Whole organisms can be used. Whole organisms tend to give great responses because of a couple of things. One, they have lots of antigens on them. Again, remember there's a lot of variety in our haplotypes, our HLA types. So some of us may not respond to a individual protein. So if I give you all a protein versus a whole cell with lots of different potential targets on it, that whole cell vaccine always works better. Almost always works better. So one of the strategies is use a live attenuated virus, and that's the case in all of these, or an inactivated or killed virus. So these are actually a strain that is not virulent, but it's still alive in these cases. And that's why a lot of times, you'll have inflammation, you'll have slight cold-like symptoms because you're getting a virus. And in a lot of cases, it's a live virus, even though it's not a virulent strain. And so, and those work really well because they make different proteins at different times. Again, remember, viruses have different stages in their life cycle. So this is going to really induce lots of immune responses against different targets that are expressed at different times. Inactivated, so you're basically killing the thing. You're kind of killing it at a time where it's only expressing what it's expressing. It's not going to continue to divide. It's not going to have different life stages. But you definitely don't want to give somebody cholera. We probably haven't been able to find really good attenuated versions of these, so we tend to want to give people pretty safe. We can heat kill things. We can treat them with fixative agents, which will bind them, or we can damage their DNA. We can irradiate them. So there's lots of ways to inactivate cells and immunize them. Purified macromolecules, toxoids, diphtheria, tetanus, these are where you take a whole big, really large toxin protein, and you're actually immunizing the person with that protein. In recent years, we've started using DNA vaccines and recombinant vector vaccines. And these are ways of getting, instead of giving the protein, we're giving DNA, which might be nice and stable, might be better to take places. And that DNA is injected into cells. That's going to be transcribed, translated, make the proteins within the cells. That might be better at inducing helper cell response or as cytotoxic response because it's made already inside the cell, ready for to be presented. We can also
You say the DNA is better for the T cell, pH and the TC?
it can be. If it works well. So you can make the proteins you want. You can have your own cells. You can have professional antigen presenting cells express this. You can have epithelial cells express this.
How do you
And you
inject
could also-
antigen? How do you inject the DNA?
In some cases, they'll coat very tiny gold beads, so real expensive. Tiny gold beads, they'll coat it with DNA, and then they'll shoot them into your cells. So it's by force, by sheer blunt force.
Like electroporation, to just shoot in the cells?
No, it's more like kind of a blowgun, I guess. Yeah.
It's not an option yet, right?
They have had them in trials. I don't know if they're and I don't know if they're openly, actively being given yet. Vectors are another way, like viral vectors, to deliver basically mimics natural infections. We're also using different non-virulent strains of viruses to help deliver, and so
So
it
you
acts like
mean like lentivirus?
yeah, you can use lentivirus, for example, to help get it into the cell, and it will express it and other genes that will help to promote an immune response. If we want to drive a Th1 response, maybe we can make that cell secrete interferon gamma as well. So in the vector, we could express not only the antigens we want to present, but we could also express the cytokines that are going to drive a Th1 versus a Th2 because a Th2 isn't going to fight it, whereas a Th1 is. So again, they all have pros and cons. Live attenuated viruses, pros, it has lots of ability to replicate, promote both humoral and cell-mediated responses. So you're going to have lots of antigen. Oftentimes these don't require booster shots because you get such a robust response. Cons are it could mutate back to a pathogenic form. That's not good. That's why we don't give live flu vaccines because the likelihood of that is very. So they're attenuated. So they're not live. These may have more side effects, complications. These also require this cold chain for stability during transport. If you want to keep a cell alive, even though these are robust cells, you still have to keep them refrigerated. That's why we have a cold season. For example, some viruses just like it cold. They survive better in the cold. In cold, well, in the case of the flu, it's cold and dry. So if you want to prevent getting the flu, keep your house humid. Florida, that's why we don't have as many flu incidences in Florida, because it's so darn humid in Florida. So us as opposed to Minnesota or something, they're going to have a lot more flu than us. So inactivated or killed vaccines, these guys are heated or chemically treated to inactivate them. So they cannot revert to pathogenic form because they're dead and they're not going to, even if they were to take up somebody else's DNA or mutate, well, they're not going to mutate because they're not replicating, and mutations always occur when you get replication of DNA, and because you don't have replication, they're not going to revert, and even if they take up somebody else's DNA, they're not dividing, they're not going to become pathogenic. So these are more stable, easier to store and transport. You have killed the cell already. What's transporting it without refrigeration going to do? Probably not a whole lot. So these are much better for giving to everybody. These often require booster shots. They don't replicate in the host, so they don't induce cell-mediated immunity, usually humoral only. There are some groups that are working on improving these types of vaccines, trying to basically target them to using nanoparticles to target these to dendritic cells. The dendritic cells would take them up, and then you would be able to get a cell-based response because your APCs have recycled these. But in general, if you don't do something like that, they don't tend to induce cell-mediated immunity. There is some manufacturing risk to personnel because you're not working initially with an attenuated strain. And so those people who are growing it before they kill it are around it before it's dead. So there is some increased risk. Because we are oftentimes using chemicals to fix it or to kill those cells, we're also adding adjuvants to help boost an immune response. Or requiring those can be toxic. A lot of vaccines, they try to remove those. Formaldehyde-based vaccines where they're fixing something. Formaldehyde, they try to inactivate the formaldehyde. It tends to be fairly safe. That was initially, a lot of people believed that an increase in autism was being caused because of these agents, but studies have shown that that really isn't the case. And newer vaccines, they've done a really good job at actually minimize, even though they haven't been shown to cause autism, they're minimizing how much of those fixative agents like formaldehyde are actually active in the vaccine themselves.
I was going to ask if the potentially dangerous or pathogens, is it due to like a local careless or local culture's ability to overcome carelessly, or if it's just the actual pathogen that's inactivated or not?
It's just basically due to kind of a numbers game that because we are fixing there could potentially due to either we didn't treat them long enough or one virus got out that didn't get fixed, didn't get bound to the formaldehyde, for example, and it could, the potential is pretty low, but there is still that potential, just statistically speaking, so it's not, it could be due to bad practice, but again, regulations are pretty tight on these type of things. So a lot of time it's probably in how they were handled if you get any that escape that. And I can't think of any time recently where we've actually recalled a vaccine because it was causing infections. There may have been, I'll have to look up and see if there has actually been an incident. Subunit vaccines, these are like your tetanus toxins. They take an inactivated exotoxin or toxoid and they'll purify it, inactivate it, and give it to you to boost immune response, a humoral response against those. So the pros are it's not going to hurt you, it's not going to infect you, it's not an infectious agent. The cons are it's not going to induce as robust a response is all. That's, for example, your tetanus shot. That's why you're supposed to get a tetanus shot every 10 years, I think, 10 years, somewhere around there.
10 years.
10. So, you want to basically, you have to, it's not going to be as robust a response. And so therefore you have to get boosters. And those tetanus shots don't feel so great. So it'd be nice if they could do something better about that. There's different vaccine strategies that we're coming up with now that are way better in some aspects. Recombinant vector vaccines. So you give somebody a vaccinia virus, you have a vaccinia promoter, and then you would put in DNA that would code for a gene from that pathogen, and then you would use in these cases, it's going to be an active form of the virus, but it's not going to have the genes that will help it replicate. And in some cases, they will also irradiate them to make sure that they're not going to be able to replicate, and then they'll still be able to infect cells and insert DNA, but they won't be able to be infectious, and you'll get expression of those genes within the cell. The pros are all the benefits of an attenuated vaccine, and fewer risks. You're not using the actual pathogen, but something else entirely. And some of the attenuated vaccine problems are still present, especially stability issues, because the virus has to be able to actually infect a cell. And we are using viruses that are most of the newer designs to these therapies, the viruses are viruses that aren't going to, the genes we're putting in aren't going to be introduced into our genome, which some of the earlier cases were, we were using viruses that actually integrated the DNA into our own genome, and there was the potential that they could actually, because they inserted randomly, they could actually knock a gene out when they inserted, and so there was that danger. But most therapies are not using those types of viruses.
Do we use the vaccine? Do we use this vaccine?
Yeah.
Like which vaccine do we use the vaccine?
I think they're using it to treat tuberculosis, but it's not for a vaccine, it's just to give a gene. So gene therapy, there are gene therapies using vaccines. I don't know that there are vaccines using vaccine just yet. So DNA vaccines, you have a plasmid carrying the gene, and instead of having a virus inject it, so now we're just taking a plasmid. We're not taking a virus to introduce it in the cell. We're actually going to put it on a particle. Host will take up the DNA, so we can put it on nanoparticles that are maybe phagocytosed. And so this way we can target it to phagocytic cells. Those tend to be antigen-presenting cells, which is great, because in order to induce a response, we need cells that have co-stimulation. They have these factors that are induced immune response. So you get antigen presentation via MHC class 1, stimulating CTL production. So that's the advantage of this, is you're already getting it into the cells that are supposed to present this normally to the immune system. The pros is it induces humoral and cell-mediated immunity, prolongs expression because they're in cells, their own cells that are going to continue to make them over time. So they have kind of, it helps, they're similar to live vaccines, and these are stable and customizable, so you can put different antigens, multiple antigens, and the cons are unknown at present. Too new, we haven't really.
May not work.
Well, we'll see. Other vaccines are conjugate or multivalent vaccines can improve. So sometimes you have a target and you say, hey, I know this is a target, but it's really not very good at inducing immune response. You can help boost that response by coupling it with something you do know that does boost or provide a good response, and just so you can kind of help to induce stronger responses by coupling them to something like a toxoid. So you can also link weak antigens with a stronger one. It might not give the desired outcome. It might be good at antibody induction, but if you want a CTL, then you need to target that to be taken up intracellularly. So we can use, for example, form these. You have to deliver the antigen into the cell for presentation on MHC class 1, so you can create these lipid carriers, and these are known as immunostimulating complexes or isotomes for delivery. And so the vaccine itself would now target itself to, similar to a virus, and it would integrate into the cells that are going to present it and be a class 1. Another thing that's important is adjuvant. So you might have heard the term adjuvant. So most vaccines will also include an adjuvant. This is to help provide that danger signal. So this is where vaccines differ from just your regular allergy shot. I can give you allergy shots. I'm trying to give you allergy shots without any adjuvants because I don't want to induce a type 1 response. I want to induce tolerance. So if we were to give vaccines without adjuvant, you would have a lot more danger of inducing tolerance, which is not what we're going for. So an adjuvant is going to be something, bacterial glycoprotein, something that is going to say, hey, this is going to help induce innate immunity and kind of get this inflammation going and start. And that's why most of our vaccines kind of cause red. Again, that red and swelling in the area because we're causing a local kind of infection. We're causing inflammation. We're promoting inflammation. So you're going to get recruitment of lots of cells into the area. That's where the swelling comes in. You're opening up blood vessels. You're dilating them. You're causing fluid to come in, edema. A lot of these are also involved in slowing down antigen release, which is the case in LPS or a lot of these oil or lipid-based adjuvants help to kind of cause the antigen to be slowly released as opposed to just disseminating and throughout and not having a good local effect, because we want a local effect. We want a lot of cells to come in there and communicate and help boost an immune response. So they can help. Alum is good at stimulating Th2 but not Th1 responses. MF59 is oil and water emulsion, slows antigen delivery. And so if you ever go into research and you have to give one of these, you basically will emulsify between two syringes. You'll basically move this oil solution with the antigen back and forth between two syringes and just mix it up, just kind of like you make with salad dressing, basically. And then SO4, alum plus a TLR4. TLR4 agonist is going to induce a Th1 response. So again, we may want to drive, this TLR4. So remember, these TLRs are going to bind a lot of times to pathogen-associated molecules, and these TLR4, if you signal through TLR4 with this agonist, it's going to now induce a Th1 response. There are other methods under investigation. And a lot of times the whole vaccine will already have these PRRs. They will already have these pathogen-associated molecules. They have lipids, they have glycoproteins that are pathogens because it's a pathogen you're giving. So a lot of times if you're giving a live cell, you don't have to give an adjuvant. If you're giving a toxoid, you have to give an adjuvant, unless you already had an immune response. So a lot of these single agent vaccines will include an adjuvant with them. That's why, again, let's bring it back to something we may all know. That tetanus toxoid is like a peanut butter shot. If you know that's a big needle, it's not a small needle they're giving it to you. They have to give it to you with a big needle because it's got this oil water emulsion in it, which causes a slower release of that toxin, but it's not much fun getting that shot. Okay, so that's pretty much this chapter.